Hi, today we are going to talk about the Intel Alder Lake architecture, specifically focusing on the central processing unit and the register set. Let's start with the brain of the operation, the control unit. In Alder Lake, this isn't a linear process. It utilizes a sophisticated out-of-order execution engine. Instead of waiting for tasks in a straight line, the control unit schedules instructions based on the data availability. It retrieves this instruction from L1 cache using a massive 6 decoder. This means it can translate many instructions into micro-ops simultaneously, drastically improving speed. Once decoded, the work moves to the arithmetic logic unit, ALU. This is a very wide execution engine featuring 12 execution pods. This allows the CPU to divide tasks. Some pods handle simple integer addition, while others specialize in complex AVX2 vector math. To tie all these components together, the P-cores, E-cores, and the graphic Intel use a high-speed internal highway known as the ring bus. Registers are small, lightning-fast storage location. Alder Lake actually use register renaming, meaning it physically has more registers than the software sees, which prevent bottleneck when different programs fight for resources. There are 4 key types of register you need to know. First, general purpose register. We have 16 of these. They hold the data which the ALU is actively working on right now. Second, the RIP, instruction pointer. This holds the memory address of the next instruction. It tells the CPU to fetch decode from next. Third, the instruction register, IR. This holds the current raw binary code, while the decoders break it down into micro-ops. Last, the status register, RFlags. This tracks the state of processor using flag like the 0 or carry flag. The CPU checks this flag to decide which path a program should take during conditional branches.
Alder Lake uses a modern ring bus and system agent design, but it still has the same basic bus rules: address, data, and control. The address bus is one way the CPU uses it to tell the system which memory or device to access, supporting huge memory sizes up to 128 GB, DDR5 or DDR4. The data bus is two-way, carrying instructions, numbers, and files between the CPU and memory or devices. The control bus acts like a traffic manager, telling memory when to read or write, handling device requests, and keeping the CPU core synchronized. Here's how it works. A P-core sends an address and a read signal through the ring bus to the system agent. The agent translates it into a physical RAM location. The RAM sends the data back via the data bus, and the integrated memory controller puts it on the ring bus for the CPU to use. So basically, it's a fast, organized system for sending and receiving data between the CPU and memory. Cache memory is a small high-speed memory located between the CPU and main memory. Its main job is to reduce the time the CPU waits for data or instructions by storing frequently used information closer to the processor. This helps the CPU run more efficiently and boosts overall system performance. Modern systems usually have multiple cache. L1 is the smallest and fastest, located inside the CPU core, often split into instruction and data cache. L2 is bigger but slightly slower, sometimes shared between a few cores. L3 is the largest and slowest, shared among all cores, helping reduce frequent memory access. Cache also uses different mapping techniques to organize data. Direct mapping is simple and fast but can cause conflicts. Fully associative mapping allows a block to go everywhere in the cache, reducing conflicts but more complex. Set associative mapping is a balance, letting each block go into a specific set but any line within it. In a multi-core system, cache coherence is important to make sure all cores see the same data. Protocols like MESI manage update across cache to prevent inconsistencies. In short, cache memory makes the CPU faster by keeping frequently used data nearby and reducing waiting time.
Memory and I/O components support CPU operation and enable communication between the computer system and external device, ensuring efficient data storage, access, and transfer during program execution. Computer systems use a memory hierarchy based on speed, cost, capacity, starting from CPU register, followed by cache memory, main memory or RAM, and secondary storage such as SSDs and hard disks. This structure improves performance by keeping frequently used data in faster memory. Then, memory serves as the primary working space for the operating system and running application. It allows random access to data but is volatile, meaning data is lost when power is turned off. I/O components communicate with the CPU and main memory through I/O controller, using interrupt and direct memory access to enable efficient data transfer and responsive system performance. Next, I will explain about the instruction cycle. First of all, the operation of Intel Alder Lake is based on the instruction cycle, which is the basic process used by the CPU to execute program instruction. Although Alder Lake uses a hybrid architecture with performance core and efficiency core. Both core type follow the same instruction cycle to ensure accurate and efficient processing. The instruction cycle begins when the instructions are fetched from instruction cache or main memory. These instructions are then coded into micro operation and executed by units such as the ALU, FPU, and load units, often using out-of-order execution to improve performance. If data is needed, it is accessed through the cache hierarchy, and the result are written back to register or cache before the instructions are retired in the correct order, completing the cycle. Main memory and I/O components support CPU operation, and
An instruction is fetched from memory during the instruction fetch stage, which is the first step of instruction cycle and essential for CPU operation. The program counter (PC) stores the address of the next instruction to be executed. And in an Intel Alder Lake 12th generation, this address is used to locate it in the instruction memory hierarchy. The processor first checks the L1 instruction cache for the instruction, and if it's not found, the request moves to the L2 cache, L3 cache, and last still to main memory. Once the instruction is retrieved, it is placed into the instruction register, where it is held temporarily so that it can be decoded and prepared for execution. The PC is then updated to point to the next instruction address, ensuring correct program flow. In Intel Alder Lake, advanced prefetching mechanism and branch prediction are used to improve fetch efficiency, especially on performance core, allowing instruction to be fetched quickly and continuously to support high performance while maintaining accuracy and power efficiency across both performance core and efficiency cores. After the instruction is fetched and stored in the instruction register, the processor enters the instruction decode phase. In this stage, the decode unit interprets the binary instruction to determine the required operation, operand, and addressing mode. In Intel Alder Lake 12th generation, processor complex CSC instructions are converted into simpler micro operation. This conversion allows efficient execution across the hybrid architecture, which include performance core and efficiency core. During decoding, register renaming is also performed to eliminate false dependencies such as war and wow hazard, enabling higher instruction level parallelism. The decode micro operations are then placed into internal queues, where they are prepared for scheduling and execution.
Once the decoding process is completed, the processor advances to the execute phase where the actual computation and data manipulation occur. During this stage, micro-operations are dynamically dispatched to suitable execution units based on their functional requirements. Integer-based operations are handled by the arithmetic logic unit. Floating point and vector operations are processed by the floating point unit, and memory-related instructions are managed by load and store units. Intel Alder Lake processor employ out-of-order execution, allowing micro-operations to be executed as soon as their required operands become available rather than strictly following the original program order. This execution model helps maximize hardware utilization and minimize pipeline stalls caused by data dependency or long latency operations. To ensure correct program behavior, the processor relies on mechanisms such as reorder buffers, reservation station, and dependency tracking logic, which collectively preserve precise exceptions and maintain the correct architectural state even when instructions complete out of order. The data processing flow within the CPU is tightly integrated with the execute phase to ensure efficient access to operands and timely delivery of results. When an instruction requires data, operands are retrieved either directly from register or through the cache hierarchy, beginning with the L1 data cache for the faster access. If the required data is not found in L1, the request proceeds to lower cache levels such as L2 and L3, and ultimately to main memory if necessary. After execution is complete, the resulting data is temporarily stored in the internal buffers before being returned back to the destination register or cache during the write back stage. Finally, the processor retires each instruction in the correct program order, committing the result to the architectural state and ensuring consistency, reliability, and correctness of program execution. This carefully coordinated data flow and execution strategy enables Intel Alder Lake processor to deliver high performance, improve energy efficiency, and stable operation across a wide range of computing workloads.
Thank you guys. Thank you for watching.